You need introduction. Who will tell you? Yo. Oh, you can hide it at the bar if you want.
I've never. How do I?
I think you click on the three dots and then you do something.
So there's
Hide video. Hide.
panel, but I don't know how to get rid of this one.
I've never managed.
There's a hide button somewhere.
Really?
Press the three dots again.
In the option. Yeah.
Go video panel. No, it's somewhere else.
I thought that yesterday and it just didn't. Sorry.
Oh yeah, that one off the far right hand. Yeah. That's very silly. You're right. We should all go back to Skype. It's too late now. It's Skype got and cheated guys.
You cannot right click it.
Okay, let's try it there. Okay. Yeah, I'll start then.
So Andrés is now starting.
Yeah. Thanks a lot.
You're welcome.
Yeah. So just to recap a little bit what we saw last time on Tuesday, I think. We were discussing labeled transition systems. I gave a definition of labeled transition systems, and we were just looking at so what happens when you have a transition system when there's no post. So the post set is empty. It means I cannot get out of it. So it's an end state. And I said we can reason about these in general, but we want to have a uniform treatment of things, and there are some things that get more difficult. So we're going to introduce this transformation so that we don't have end states like that. And what we do is, so if we have an end state, something that we consider an end state, it might even have a transition somewhere else. But if we want to consider something an end state, we can add a new capture state, which is called, which we call it with this a single transition to itself. And that capture state will ensure that we'll never have something that doesn't have transitions out of it. The post set is never empty. Yes, I can give you the mic.
You can keep it here. Is it always only labeled? Oh, this on? No, it's not. Is it on now?
Yeah.
Yes. Is the end state always going to be the capture state always going to be labeled with nothing, or are you going to add a label for every action?
No, I think I would have a special. Yeah, I'm putting it with nothing here, but I would have a special capture action that says like a special.
Okay, so it just ignores all the action.
Yeah, you add a new action basically that you like a dummy action. Like you don't want to confuse it with something else. Right? Yeah. You don't want it to accidentally sync with something else. I guess that's right. So for the rest of this course, I'm going to assume that this thing will never happen. Well, or the one in the slide before where I didn't have this thing back. So there's always going to be successors for the transition system. So our paths will always be infinite, like full paths, like maximum paths are maximal, so they're always going to be infinite.
Andrés?
Yeah.
Is there a specific reason for this?
Yes. So yes, there are specific reasons. Some results are at least not as obvious if you can have finite paths. You usually have to make a case distinction, and I don't know if everything we're going to talk about holds if you have finite maximal paths. So, but with this transformation, like everything you want to model, you can do this transformation. So we've had these paths that are like sequences of states in the state space of the label transition system. But we don't really care about the states themselves, as I said. So if you remember, we have this labeling function for atomic propositions. So we actually care about these atomic propositions to define the properties of the system we're looking at. So we kind of want to translate these paths into words over the power set of atomic propositions. So we want to define something that we call a trace. So paths are over states, traces are over sets of atomic propositions. So if we have a path fragment pi, right? Remember, that's just a sequence, finite or infinite sequence over states. Then we can define the trace of this path fragment pi as a sequence L of I. I'm calling it L of pi. This is the name I'm giving it. In this set, I'm not going to be so consistent with it, but here I'm still trying to use the more computer science C notation of an arrow. Sometimes it is more intuitive. So from functions from the naturals to the power set of atomic propositions. So basically sequences of atomic propositions. You can think of this. And this is going to be a sequence given by the obvious thing. So the ith element of L of pi, so this trace of pi, is basically the label of the ith element of the path fragment pi. So this is for finite pi fragments, which were sequences, and for finite ones where these are words, we're gonna do the same. Basically, we just count over the correct domain. And so if we have a state S, we can define all the traces starting from S. Yes, go ahead.
So we're going to observe that no atomic positions hold for a while, so we can kind of see the passage of time, but not this.
Yes, absolutely. So it can and will be the empty set a lot of the time if your atomic propositions are sparse enough. So for us, if we have a state S, we want to define the set of traces of starting from that state, which is basically, I didn't write this formally here, but you know what I mean. Basically, starting from S, you take the successors of S, and so all the path fragments so that pi 0 is S basically. And if I take the union of the initial ones, then that's the traces of the transition system, right? Because these are the sequences of atomic propositions that you can get from the transition system. So these are basically, this is what the executions that can happen in the system we're trying to model, but we're forgetting what the states mean, and we're just concentrating on the atomic propositions that hold there, because that's what we want to talk about. So just to give you an example, if you remember this traffic light example where we had 2 traffic lights, one for cars, one for pedestrians, for walking, and we had this how it feels like if you go to the street here. It's always cars, green, yellow, red, green, yellow, red. So this path here, or path fragment, if I ignore that. So the dots corresponds to the atomic propositions. I mentioned we had 2 atomic propositions. Cars can go, pedestrians can go. And so if it's green and yellow, the cars can go. It's the only atomic proposition that holds. And if both are red, then nothing holds. So we have the empty set. So we're just translating this to the atomic proposition. There's not much more to it, but it's important to talk about this translation because that's the point of atomic propositions. It's what we want to talk about in this state. So just to close up this basic introduction to the objects that we're modeling, LTSs, there's many ways of reasoning about when 2 of these are equivalent. Today I'm just going to talk about one, which is the one that relates to the things we've just defined, which is called trace equivalence. And if we have 2 transition systems with the same atomic propositions, you can generalize this and have those subsets and specify trace equivalent with regards to which. But here I'm just assuming they're the same. So we can say TS1 and TS2 are trace equivalent if their set of traces are the same. So remember, we just defined this as all the traces starting from the initial state. So if the set of traces starting from the initial state are the same, it means the same executions happen, at least with regards to the atomic propositions we care about. And then we say these two transition systems are equivalent with regards to that. And as you're going to see later, this means the propositions we can make about these systems and the logic we're going to learn about, they're equivalent for these 2 systems. So there's more interesting notions of equivalence, but that generalize over more complicated logics. But for the things that we're looking at now, which are these traces, this is the easiest notion of equivalence. So yeah, that's the basic idea of labeled transition systems that we had. So now we know. Yeah, okay. I added this because someone asked last time, and now they're not here, but maybe I can tell them afterwards. A lot of the definitions come from these 2 books. So Principles of Model Checking and this handbook. This handbook is really nice. It goes into more depth, and this is more general. So if you want to read more about this, these are my main sources. But yeah, going back to the material. So we've seen how we can mathematically describe these. And today, because I want this to have somewhat applied flavor. Sorry, yes, there's the question.
So just to check, so this set of traces, is it finite?
No.
And the length of the traces, is it infinite?
Yes.
Okay.
Because we're assuming that all paths are infinite because we did this transformation.
Yes.
So that's why all the traces are also going to be infinite sequences.
Yes.
Like indexed by the number.
And the set of traces, what you're saying is also infinite.
Well, that depends on the system. If my set of atomic propositions is empty, then I just have one trace, all empty set. That's a boring case, but
okay.
But so it depends. It depends on the transition system. Yeah. But
Yes.
in most cases, it would be infinite. Yes.
Did we require? Oh wait, did someone else know that? Did we require the set of states to be finite or not? I can't remember.
We didn't require the set of states to be finite. If the set of states is finite, the set of atomic propositions is finite, and the set of actions is finite, then the label transition system is finite, then we can do model checking. But for the definitions we've done, we didn't require that. But in practice, we do want that to be the case.
And so if you have a finite label transition system, does that give you a property that traces eventually repeat, or is that false? So they do eventually repeat?
Yeah.
Okay.
They do eventually. Yeah. Because traces are traces are linear properties in some sense, and so you yeah. Basically, we're not going to cover this, but yeah. So right. So this was the way how you describe this mathematically, but a lot of the times you don't want to like encode these label transition systems by hand. It might be tedious. So we're going to talk about modeling languages, which are basically programming languages which have semantics, semantics label transition systems, so that we can reason about them in a way like we want to reason about label transition systems, but give us an easier way to describe the things. And I'm going to talk about Promela, which is a modeling language. It's a well-known one. That's why we're going to cover it. There's other ones, and that it's like with programming languages, they're different for different uses. This is the one we're going to talk about. So what's the core idea of these kind of modeling languages? The core idea is we have some sort of formal language L, and as I said, we have semantics of them as label transition systems. So we're interpreting them as some sort of mathematical object. So that's why I'm using this denotation symbol here. This is a diagram, so it's more informal, but you can define this. So label transition systems are going to be the denotation of this modeling language. So we can describe our protocol in this modeling language and then translate it to a transition system, to the mathematical label transition system through this semantic function, and that's what the compiler or the model checker does. So Promela is the language of a model checker called Spin. It's a very mature one, so it's been under development for over 30 years. I think this year they had the 30th symposium on this. So that's got its positive and negative sides. And Promela stands for protocol meta-language or process meta-language, depending on where you look at. It's got a C-inspired syntax, as is maybe less surprising by its age and use case. But I think we'll manage. So this is a very simple example of a Promela program. Interesting here is this init keyword. So if you remember, we have initial states in our label transition systems. We also want to be very explicit about how does our system, the thing we're modeling, how does it start? So it starts with this init keyword, and you have expressions, at least you have arithmetic expressions and logic expressions, like you'll know them from something like C. So we can, for example, define an integer, which we call num, and it's this product of some numbers, and you can actually use even the C printf function if you want to debug things. This is just because to have the obligatory thing, and then I could just call spin, which is the model checker, on this example, and it'll actually run this and print that. And this happens to be the composition of 2024. So this is a very boring program in the sense of Promela, because it's deterministic. There's just one thing that can happen. But it's just to warm up. It's the obligatory hello world. And what's happening when we call spin with this is that it's basically compiling. It's generating a piece of C code, which will then compile with the C compiler to build the checker for the specific properties that we're asking it to. In this case, nothing. So a more interesting example here. Again, this has a very C flavor, so we can also define preprocessor macros in the way that we all know and love. And here, this is perhaps the most important definition or keyword in Promela is proc type. So proc type allows us to define a process or a template of a process, right? You can think of it as a class or as whatever your favorite notion is for this. And so we're defining one that's called counter here, and it can take parameters. So we're taking an integer I, and here, which is the initial value. So here, this is a very interesting concept for Promela. These do loops. So do odd says do whatever it is in infinitely often, right? It's like a while one, something like that. That's the way to think about it. So it repeats this indefinitely. And then we have here guarded actions. So these colon, colons, colon, colon is a way to do a guarded action. So it'll try to execute the first statement. And if it succeeds, it continues. So this will check whether I is less than n. And if this Boolean check succeeds, it executes this. And the same here for greater or equal. And so this increases the value. And if we're above equal or above to n, we break. So this is kind of, again, this is actually not what Promela is intended for, but just to introduce the concepts. There's a question there.
Yep. Are these? Oh, yeah. So,
are these statements like sequentially processed, or if there are several like enabled guarded statements, is there a non-deterministic choice?
If there are several enabled guarded statements, there's a non-deterministic choice, and that's the crux of it, because that allows us to define multiple outgoing transitions of something. Yes, and also this arrow. So arrow and semicolon are the same. We're using arrow here because it looks more natural, but arrow and semicolon also have the same semantics. It blocks, and when that happens, it does the next thing. Just the guarded statements will try to execute the first thing. For something else, it would block as soon as it does, but things can happen between them. So you're interleaving between semicolons. And for init, we can run the counter with some initial value, and this will just count to 100. One thing to notice here, if you remember this construction that we had, that there's an end state, we want to make sure that we know when something is an end state, a capture state. So this is a label end, and if you find this special defined labeled, then we know that's an end state. That's fine. So it'll construct this capture state, or in this case, terminate. And here we have another statement skip that just does nothing. So these are, again, this is as a thing to check. It's very boring, but it helps understand the core concepts. So maybe we can look at something, an example we've been looking at, so that it's a bit less boring. Is the traffic light example that we had before. So this is the two traffic lights conjoined already version. So here we have this M type. M type is some sort of enumeration. You can think of it as an inductive type without the inductive case. So without being able to recurse, or as a C-enum, whatever you prefer. And we can define these three states, red, green, and yellow, just give them names. And now I can also define global variables. These global variables are just going to be global to the entire system state. And we can now define the traffic light with this M type of enumeration. So this is the transition system we saw before. Right, so we're gonna indefinitely do one of these non-deterministically. If both traffic lights are red, then the car gets the green light. If both traffic lights are red, then the pedestrians get a green light. So you see here is the same condition twice. There's going to be a non-deterministic choice. One of the two is going to happen. And again here, red and the pedestrian traffic light is green. Well, then it goes back to red. There's no yellow for that. And here, green to yellow, yellow to red. So an interesting thing we're doing here too is we don't have an init statement, but we have this active prop type. That's just a way of saying, okay, initialize this, and this is going to be, right? It's just syntactic sugar for that init underneath. But that's the way we would model the traffic light example that we had before. And this is the transition system. You can check. I should have flashed that earlier. But if you remember, we motivated this construction as well by saying we don't want to build these huge systems like already joined together. We want to compose them of smaller parts. So we have this composition operator, probably handshake composition operator. We want to do the same thing with our modeling language to be able to compose it in small pieces. So we can use a channel for that. So this is the explanation of the M-type name. It's message type. And the idea is that we can use this as the message of channels. In this case, we're not going to use it as the message of channels, but we can declare also a channel, which is the button press, right? Remember, you have the pedestrian traffic light and you press the button if you want to walk. So we want to model this as a channel. And it's kind of a quirky syntax. So ignore this size of 0. We're going to come back to it. It's just saying I cannot buffer these things. I cannot store them. But the type of the channel is Boolean. So we're going to have something to send Boolean messages between two different processes. And so we can define the pedestrian button using this channel here. Again, here it's active proc types that I don't have to instantiate it in the end. And the button, it's going to do one of two things non-deterministically. We're just modeling the button and not the pedestrian. So it's either non-deterministically going to send true or false. And to send a message, we use this exclamation mark punctuation, like Sam called them yesterday. So you have press, send this exclamation, like this piece of syntax says, to channel press, we send the value true. This value could, of course, be a variable. Here, I'm just using a constant. But we're going to send this value through this channel. And here, we're going to send this other value. And because it's there's no condition here. So this will always succeed. Something when you want to send something. Well, it will always succeed if the other person's waiting. So it's going to just do one of these two non-deterministically. And then on the other side, the traffic light wants to receive the button press. So this is how I chose to model it. It's not the only way, but we have this Boolean local variable to the traffic light that says, have I seen a button that's been pressed? And then we do non-deterministically the three things that we did before, right? Just continue to update the traffic light. And here's the interesting change. That's how we receive the message. So you can, if both are red, then we can receive a message from the channel press, right? So this is the dual to the exclamation mark is the question mark. And the thing with the question mark is we have to receive that into a variable. So that's why I had to define this variable before. So this cannot be an expression that's going to be checked. So this has to be a value. And just like we had the do clause, we have the if and phi clause, which does the same thing, but just does it once. So this is not going to repeat. This is just going to non-deterministically choose one of the guarded actions here. That's where the guard is true. So in this case, it's just like you'd expect a normal if, because these two are mutually exclusive and cover everything. So if the button is pressed, then the pedestrian traffic light goes green. If the button is not pressed, then the traffic light for cars goes green. So that's the syntax we use to define this communication. So this is asynchronous communication because both of them have to be sending and receiving at the same time. And this is the handshake. This is essentially the handshake that we were modeling before in the transition systems. So remember, we have this this modeling language, and we want to go to the label transition system. So the way we kind of, I like to think of this, and the way we can kind of reason about how we build this label transition systems from the modeling language is that we have some sort of intermediate representation of the transition system that's built by the program. That's so the notation of this language is not the LTS itself, but it's this program graph. And out of this program graph, we can build a transition system using some other function, TS. And I'm not going to give a full definition of that because it's very specific to how you choose to model ProMeline. I think it'd be too distracting, but I kind of want to give you the core ideas of how you want to do this. So you want to build a label transition system out of your program graph because this is very dependent where in the program you are. So you want to model the location of your source, of your program explicitly. So what's the program location? And then you want to look at the values of your variables. So what's inside, if you have a context gamma, what are the values of in this interpretation of your context? So this is also very very natural in my opinion. What the state of the system is basically the program counter, where in the program where's the execution, and what are all the values of the state, right? And the idea is you want to have these conditions that are propositions over your variables in context. So you want to define some sort of conditions to talk about everything that you have in scope, and we call this gamma. And then you can define some sort of conditional transition relation, like looks like an injection here, hook right arrow. But so if you remember in the original case, you have the actions index a relation over states. In this case, it's a relation over locations that is enabled by the value of the graph. So the way you make the dependency of the state is explicitly through this condition. And then you can define like the normal transition relation of your label transition system with a rule that looks sort of like this. So if you have this is not a capital I, it's a lowercase l. So if you have a location L that goes to location L prime with this guard G and action alpha, and also we can interpret these guards as some sort of propositions in some propositional logic. So if this guard also holds, so it's a model for the state eta, then we can say the location L and the state eta transition with action alpha to the state L prime. And then we kind of want to interpret the action. The action is basically, in this case, is what's happening in the program. So at that location, we want to build the alphas of this program graphs to be the statements in the language. And so we can interpret the statements in the language and then apply them to the guard. So that gives us the new state. Basically, this is what updates the state. It's just the way I'm choosing to write. What updates the state is just the denotation of the guard, the expression that's doing here. Sorry, of the action. So I hope you can kind of see how you could use this to build a label transition system out of some structure that you easily built from the syntax that we're writing here. So we have this channels, but we said that these channels are going to be 0. I'm going to model this other example, the one with the questionable atomicity, and we have this. In this case, we have, so if you remember, this was two processes communicating. They want to set a flag when they're going to enter the critical section, and then they go out. Just also for context, like on Tuesday we said it, and someone pointed out one of the flaws that was on purpose. So this is basically Peterson's mutual exclusion algorithm, but you're not actually arbitrating between them. So if that doesn't mean anything, don't worry. So the idea here is we have these flags, so two flags that each process uses to enter their critical section. And just to introduce a little bit of the syntax more now, so that you have a flavor for Promella. Now we can say, well, I don't have one proc of this type, but I have two. So we can use this notation to initialize two processes at the same time. And here, this is the code. So basically, this is, again, relatively boring. Just do this all the time, all over again. So that's the way you could model some sort of sequential composition of programs in some language that corresponds to this subset of here of Promella, that like basically this intersection of Promella and C. So what's happening here? This is the code that we had first. So we can use this special variable _PID to refer to oneself. So if you remember on the graph, on the picture, we have this square, like this triangle brackets, self and other, to kind of parameterize, are we talking about ourselves or someone else? We can use this _PID the same way. So PID is going to be 0 and 1 for the two processes we instantiate here. So we can say, well, I set my flag to 1. And if the other person's flag is 0, then I can go into my critical section and then set my flag again to 0. So what's the critical section? We're not doing anything. We're just keeping track of that with this byte, basically saying how many processes are at this time in the critical section. So if we enter, we increase it. If we leave it, we decrease it. And here we're using semicolons because it looks more like a program, but remember this and this are essentially the same. So it's going to interleave between any two of these semicolons or arrows, the model that we're building. So I'm just going to give you a bunch of examples so that you can see how this is useful. So I hope you'll indulge me. Another example here. Yeah.
So I'm just curious, how well does the tool build a efficient model of, because looking at the code, it seems like it might be quite verbose. So in the sense, by verbose, I mean, how can it distinguish between, okay, this is one state and this is just code that I'm performing, and so does it build, is the building of the model like exponentially large?
Yeah. So I think I know where you're getting at. If after this example you still have that question, then please ask it again. But so I mean, there's some inherent complexity. Of course, it's gonna grow up. But if you want to not unnecessarily grow your logic, there's a good way to do that. That's what I'm going to talk about now. Okay, so yeah, I'm trying to introduce this slowly through different examples. So you'll have to indulge me with the what's happening here, so that we see how we model it. So this is, again, as I said, if you remember, we had this channels being synchronous. So you had to have both processes talking at the same time. But if you want to reason about networks, for example, then this is very unrealistic. You're not going to wait until they're both handshaking and then send a message. In most cases, you want to have some endpoint send a message through a router to the other endpoint, right? And usually between these different nodes in the network, you're going to have buffers where you can store messages. So if I want to send something from A to B, this endpoint to this endpoint, then I'm just going to send it through the router, and the router is going to find the other guy. And while things are here in flight, more packages can come, etc. So you have these buffers so that you can deal with multiple things incoming, things are being slower in between, etc. So if you want to model some sort of realistic network, you want to also model the route between them and the buffers being full and these kind of things. So we're going to model just the network in this case. So we have two endpoints, two routers, and buffers between them. And here we're finally going to use these M-type thing as an actual type of a message. So very simple. We have a request and we have a response. And for good measure, we have no message as well, because we want to maybe model this. So what does the router do? The router is the simpler one of the two. So the router will, I mean, here we're making essentially, like, we're parameterizing it with the channels, because we can have, if you remember here, we have two routers, so I want to instantiate them with different channels. And at the beginning, there's no message. And then the router, what it will do, it'll read from its incoming buffer, and then it'll send it to its outgoing buffer. In this case, the routing algorithm is very simple because there's exactly one entry and exactly one out point. Of course, this could be a more complicated routing algorithm. What does the endpoint do? The endpoint is the interesting one. Again, we can parameterize it by the channels that we have, and we start without a message. But now we have this do loop of the things that it can do. And here's the keyword that I hope is what you're asking me. So this keyword atomic will tell me, do all of this as one step, right? Don't interleave between these things here. Just do it atomically as one thing, because I don't care about these interleavings, or because my model actually assures me that this is atomic. I want to assume that this is atomic, right? So, for example, what's happening here is, okay, if I have no message in my endpoint, right? I'm not dealing with any message that I've received, and this is a weird piece of syntax in Promella. If we have the question mark, but we put this square brackets, it's a Boolean check. Is there any message in my incoming buffer without receiving it? So if I'm not dealing with anything and there is a message that I could receive, then receive it. Why do we do this atomically? Because we don't want to block on receiving something when there's nothing there, right? So receiving from a message is blocking. If I just had this, then it would start with an empty buffer. It'll choose, okay, this thing is activated. I'm not dealing with anything. Great. So I'm going to the next one, and then the next one blocks because there's nothing incoming. So you'd get a deadlock immediately if everything's empty. So what you can do is you can use this atomic keyword to say, well, all of this has to happen at once. And so now the guard says, can I execute the entire thing? If I cannot execute the entire thing, then I cannot execute this arm of the do.
So why do we have to write in the brackets the message, like the MSG? So if it's, okay, it doesn't really matter.
Promella syntax.
And
I don't know.
okay, and when you're saying interleaving, do you mean it like in the sense that you defined last week? Okay.
Yes.
Sorry,
On Tuesday. Yeah.
You know.
Yeah. So I mean exactly in that sense, interleaving. So this is going to be one step of my relation right arrow. Right. So this whole thing is going to be one transition, and not going to be breaking. So normally this arrow, the semantics of this arrow is, this is going to be a separate transition, right? I do this, and after this is one transition, and this is the next transition, right? But if you do atomic, then you interpret this as sequentially all of this being one transition. Okay, so that's the most interesting arm of this year, but just for completeness, we can look at the other two. So if there's something, if I'm not processing anything and there's something to read, I'll read it. If I'm processing, I've just received a request. So this is the message that we have locally. If I just received a request, I want to respond to it. So here we can send a value, right? Remember, for read, it has to be a variable, but here we can also send a raw value. So we're gonna send a response, and we clear the message. And this we also want to be atomic. We could decide not to make this atomic, but we decide to do it. And again, here we want to atomically say if I've received a response, great. I've done it, I can consume it, so this disappears. And finally, I can, out of nothing, decide to send a request, right? This is non-deterministic modeling. Whoever's behind that endpoint, the endpoint says, oh, now I want to send a request. So these are the four arms that model the thing that we have. And we'll see later what properties this has. So that's why I'm walking through the entire thing, but also so that you get a feel how you could model this in a language like Promella. So we talked about the semantics of these process graphs. We want to talk about how these channels work because they're built-in primitives in the language. We could build them using the rest of the primitives, but they're convenient to have as built-in. So how can we, for example, try to define semantics for that? Again, just the core idea. We can add, we have the set of actions that we had, and we can extend it with a set of communication actions. And again, this was a question on Tuesday. How do you make sure that the synchronization works? So we have these communication actions that just say, okay, I'm sending, I'm receiving from a channel. And then in this set, we have these actions to send a value v and to receive on channel C and to receive into variable C. And so we can have these program graphs that we had before, right? Like this intermediate representation. And we can compose them by building corresponding actions of these pairs. So when someone's sending, so if I'm sending a value v to channel C and receiving that from channel C into variable v, this is one action, right? And this is the same action on both sides, so that they can handshake in the way we defined handshake on LTS. I hope that makes sense, at least intuitively, as like, hey, how could we go about building this label transition systems out of the syntax that we are showing here also for channels. And then if the channels have space, then we also model that. Okay, so that's how we model systems. So far, we've seen what kind of protocols, what kind of systems we can model with this mathematical structure of LTS, and how we can build it using modeling languages, specifically Promella. But we haven't talked about the properties that we care about at all. So now I'm going to talk about the properties that we maybe want to discuss. But before that, if there's any questions to label transition systems, modeling languages, Promella, then this would be a great time to ask them.
How do you know that the translation from the Promella into the cryptic structure does the thing you wanted to do? I mean, what's the correctness criteria, so to speak?
So you mean like in the sense of
you
what's the
write down
TCB
code.
or?
Yeah, I mean, you write down the code in Promella and then you
Yeah.
generate it, and then how do you know that this generated system is kind of
Well, you have to have spin in your TCP. You trust that spin does the right thing.
I see.
And you could technically inspect the generated C source because it builds. So as I was saying, you take this Promella syntax, piece of syntax, and you build a new program, a C program that models the system and checks the property that you're looking for. So you could do some sort of translation validation thing where you look at this generated C source if you wanted, for example. But in general, I think people basically just trust that spin does its thing and it's part of the TCP.
Thanks.
So I think this is what we were talking about offline, but I'm going to ask the question because I want to make sure.
Sure.
So Promella doesn't force you to build decidable models, right? As in, it doesn't force you in a space where it can decidably model check what you build. In the sense that sometimes it might not give you a result, right?
So it definitely doesn't statically check to ensure that you do. I don't think, no, so I think there's some, I mean, I'm sure there's a fragment where you can make sure that it's decidable, but I think the whole thing does have some features that let you, so the fact that you can, that an action can be instantiate a new process basically means you could instantiate processes in a, I don't know if it would, actually, I would have to check if it forbids to do that in a do loop or something like that, but I don't imagine it does. So I think it doesn't, I think it doesn't force you, but it's relatively simple to write in a decidable fragment of that. It's just not as clearly delineated, but yeah. Yeah.
So just to check, so in the previous slide where I had the model with the atomic.
The model with the atomic.
Mhm.
This, yeah.
Yes, so the things after the colon, which are enclosed within the atomic. So does that represent yes, a single state? Or so the thing before the arrow, the thing after the arrow, are those states or transitions?
Neither. They're
Okay,
so
so can you explain, please?
yes. So
Thanks.
so the thing, the point here is that we kind of want to build the states on two parts. One is the program location. So where in the program are you? So well, this would be a program location, right? Like this basically this if you think of the program pointer saying, okay, I just did this, entered this do, now I'm going to do this next statement, this atomic, that's a program location. And then the state of all variables. So that's what I was trying to say by these values of all variables here. So if you have this message, or in this case, this message here, the value of that is also part of the state of the system. So you compose it by two things, right? So you can have this message type here could have requests, or like could have had a request that it received from this. So after finishing this statement, you'd have the value request in message, or before executing this, this message should also have the value request in memory. Imagine these atomics were not here, for example. You could have the value message here and here before executing those two statements. So it's not just the values of everything that's in memory, but it's also the location in which you are. But it's again, and it's also not just the location, but
Okay.
yeah, I hope that
Yes,
that
yes,
answer
that
your question?
clarifies it. Yeah, thanks.
and the transitions you built by the semantics of these statements, right? So basically this is this interpretation here, right? So this is the state of all variables that you have here. And so the transition is, this transition label is basically the statement itself. Message equals nil, right? Like setting the message to nil, that would be alpha. And so with the transition alpha, I go from the location where I just received, where I just processed the message, where I just received the message, to the location where I just set the message again to nil. And I would take the value of message from request to nil by interpreting the semantics of the statement. That's my action, right? So the setting thing. Right? So that's why I'm writing this kind of like with this denotational bracket, because in a sense I'm denoting into the domain of whatever it is the values is that we're doing, and we interpret this as a function really on messages.
Yes, yes. So if I may, and the guard there, or that's G.
Yeah.
That's, so could you remind me what?
Yeah, so that's, I didn't really say it, I just put it here in parentheses and wave my hands. It's a propositional statement of the values of the variables in context here.
Okay.
Right, so if I have my context gamma that says I have a variable called message in scope, then I can say message equals nil. That's a propositional statement. And that would be like, just think of it syntactically, that would be this condition here, gamma. And then we can interpret this condition, right? Like we can give it some sort of semantic saying, well, my current state is a model for what models this condition gamma if it does the obvious thing. So we can kind of decide this propositional statement here. And if this propositional statement holds, then we do the transition. That's the way we interpret the guards.
And this kind of creates a new state, right? And if it does not, then you cannot transition.
Right. This creates a new transition.
Transition,
Yes.
sorry. Yes.
Exactly.
Okay.
Cool. So, right, we have 3 more minutes. So I'm just going to motivate what we're going to do with modeling properties, and then in the afternoon we can basically talk about the properties we want to model, which is great. I didn't want to start this in this morning session, so thanks for the questions. So far we've shown how we can describe these transition systems mathematically, how we can write them in some convenient syntactic way and compose them, but we haven't talked at all about the things we can say about. In fact, well, obviously informal examples, but we've also the definition of traces that I've given you also constraints about the kind of things that we can say about them, because we're just going to talk about these traces. So these traces are called linear behavior because it's a sequence of steps, and we're just going to talk about how can we make statements about the possible linear behaviors of these label transition systems. Basically, how can we talk about these sets of states? The sets of the sequences of atomic propositions linearly in the LTS. And again, we're going to use. I'm going to introduce a logic to talk about that, but I'm going to do that in the afternoon. So, yeah, I think that's it for this first morning session. Thanks.